Hello guys, thank you very much for connecting. So although we were we're a little bit late, so I have to run. So nice everyone to see you. This is the research increment number 14, and I'm gonna be quick on this. I'll be talking about a little bit the team update, some update on the projects, and also some messages that I usually say also to the lab. So concerning the team, we have had some updates. We received Carlos, who will be working basically on ergoCub, but he also somehow will be touching topics related to machine learning and try to understand how to use transformers in order to transformers or like machine learning methods in order to, let's say, make an artificial operator for our teleoperation infrastructure. This is something like in a nutshell the objective that we are preliminarily giving to Carlos, and then potentially extending it also to physical human-robot interaction, where the exeroceptive sensing might also be taken from wearables. So then we received Alessandro. Alessandro will be working on Isaac, and I don't know if Alessandro is here. Yes, everybody knows Alessandro. Alessandro arrived to be working on Isaac. Actually, there has been really a nice baptism for Alessandro, because actually the first week he arrived, we went to Tokyo. So then Filippo, who joined the Delta team, Filippo will be working on basically physics-informed methods for calibration of FT sensors, because we all know how we struggle and how painful is that. So we're trying then to understand the new modeling techniques for the FT sensors that are fundamental for our torque control infrastructure, because guys, we have to get back to torque control. Okay, so I know it's painful, but we have to get back to that. Okay, so then Shabarish is arrived also this week, been working. So if I don't know if you know Shabarish is here, Shabarish should be working on the ergoCub design. Then on the 1st of September, we will receive Marco Forleo. Marco Forleo was an engineer, I think, working for ST. And then he joined the iFeel for the work that the iFeel guys are working onto the embedded wearable system. And it would be nice to take basically a step also towards embedded AI. Okay, so then we will see a little bit how to understand the deployment of algorithms onto the iFeel chips themselves. But anyways, these are one of the general directions. So this is an update of the team. So some projects, update on projects. Last time we started talking about the renewal of Daniele Automation joint lab. So the Daniele joint lab that we were working on, which is also coordinated by iCap Tech. We have a team working on the joint lab. Silvio is the Scrum Master, and then we have Giovanni. The team is doing a very great work. It's not really easy to bring the results and transfer them onto real environment. So the team is doing an amazing job. And basically we got the contract signed for the extension. So everything has been smooth. Concerning the extension of Camozzi, this is also another joint lab that iCap Tech leads, and we are part of the team working there. But there are still issues with the IP. So the TT office is still mitigating with Camozzi in order to understand these IP issues. Then Total Spine. Back in time, last year, we submitted a project called Total Spine. The idea was to take the iFeel and give it to Fondazione Carlo Udognocchi, which is a rehabilitation center, and also to Campus Biomedico in order to monitor patients with low back pain. Last year, the project, it was nice because we scored first at the same ranking with another project. So we didn't get the project because our average age was like 1 year older than the other. So the only criterion for which to exclude us was our average age. So anyways, the long story short, we submitted the project, and actually the Fondazione Udognocchi, the Campus Biomedico in Rome resubmitted the project, and we passed the first evaluation. So we are going towards the final rush for understanding if we will get the project or not. Then we have another update. We have an ongoing discussion with an American company that I cannot disclose the results, but people somehow working and helping me on this know the details, since this is basically an open research increment. I cannot give you details, but a long story short, we have this joint lab that is starting, and the really nice story of this is that basically they knew us thanks to the Venice video. You remember the teleoperation video. So and then they started working on avatar robots. Okay, so they said, hey, but we don't know how to do these things at the application level. We have to look for someone who knows how to do it. And then they started looking on YouTube. They found us, and then basically we started the collaboration. We started not the collaboration, the discussions on how to transfer the avatar technologies that we also brought to XPRIZE to transfer onto their robot. So then, actually, there is another project. This is something we submitted last year with iCap Tech. And there is Rycam. Rycam is a company that basically does devices for cars. But they also have this research inside for bikes. And basically, we submitted a project, we forgot about the project. This is the truth. Okay. And then I received a call by Marco and said, Danny, the project we submitted actually, and we forgot about, actually passed. So we went through. It's a PNRR project, so Rycam receives the public money. But anyways, long story short, there is this idea of making an e-cargo, which is a sort of floating-based system. Okay. And then we probably have to, our specific task there is to build to help for the simulation infrastructure and control. Okay. Anyways, so we have a certain number of things going on also concerning this e-cargo. Then really quick, 2 messages, something that probably you don't like, but we are getting crowded again, so we are lacking desks. And this is somehow a contingency that we have to solve. There are 2 possible actions on this. The third one is clearly finding other desks. Okay. So the first one is that we stop the hiring, but then clearly this doesn't make sense, because otherwise we have to, these projects have to not be unloaded to the existing researchers personnel, and we clearly don't want this. The other possible option is to implement a sort of desk sharing for collaborators. Okay, so sort of that we are no longer assigned to desks, not one-to-one, but basically we have a pool of desks that will be shared. And how to decide this? Probably it's to take the average number of people that somehow don't come very often, and then we take those desks and we free them. Okay. So otherwise, there is no really threshold. So in this, I think that this way you can also understand why there is a little bit of statistics on when people come, when people don't, because we have to understand how to deal with these problems. Okay. Okay. So these are the message. The other message, I said it also the last time, but I still perceive these guys. It's important. We have to be. We do science and technology transfer, so we have to be aligned with the state of the art. Okay, you have to be passionate about this. You have to be. You have to look for the latest results. You have to read the papers. You have to understand what is going on, because otherwise we simply get not aligned with what is going on right now. We don't know. We don't know what our neighbor is doing, and this is bad, really bad. Okay. But not even somehow what is going on in the state of the art. So I want to push you a little bit in order to stay aligned with the state of the art. Okay, this is a strong suggestion that I give you. I think that I am on time on this, so it's 9:28, and we can move to the next.
Bene, ok, si sente. Buongiorno. Okay, so basically this is the vertical presentation for ergoCub, and basically I will describe the story of the work that I did in Switzerland at the Robotics and Perception Group led by Davide Scaramuzza in Zurich. The mission, Gabri already told about the mission of ergoCub, so I will repeat myself because I need a bridge. Basically, the mission of ergoCub is to fuse legged locomotion, so move through the environment using the leg, and aerial locomotion, so move to the environment. So in this case, we just designed a robot that has several jet engines and can move through the environment using legs and spine. So basically, ergoCub is the king of multimodal locomotion. The research question. What we want to achieve is something similar to what we see in this video. It's a sad video for Italian people, I guess. So basically, in this video, we can see a man that is wearing this jetpack and is flying and walking at the same time. Basically, the research question is how we can achieve such multimodal locomotion, so using both locomotion modes. In the previous episode, what I did to achieve such a behavior is to use trajectory optimization. So I wrote the model of the system in terms of robot dynamics, in terms of jet engines, and then just designed a task. And the robot and the nonlinear optimization algorithm was able to find a behavior that was able to achieve this task. Works. The problem of this approach is that to generate some trajectories is really slow, but we can use these trajectories as a library of behaviors that we can stabilize with an online controller, for example. Another approach could be to use reinforcement learning. In this case, we are totally model-free, and we are just using the environment to give feedback to the agent and learn how to accomplish a task. To setting up a reinforcement learning environment, we need, first of all, a simulator. And imagine to have a lot of clones and that you can share the experience. The training will be super, super fast. In this case, what can help us is, for example, NVIDIA's Isaac Gym, that is a product from NVIDIA, that is able to simulate thousands of agents and then share the experience and learn really, really faster. It moves from hours to minutes, for example. And in this case, we have also several algorithms to train the agent. In this case, I choose VO, that is the most famous one, most stable, the most used. So at this point, I had to move to Switzerland. And in our lab, in that lab, they are really good in drone racing. Drone racing, basically, it's a race where drones are flying super fast through these gates. On the left, there are human pilots that are on the right, there is an autonomous video in SuperQuark where they show the autonomous racing. So in this case, the policy is totally RL-based, and the drone was able to go super fast through these gates. Our question at this point was, can we move such approach to jet power robotics, in this case, humanoid robotics, to achieve something that is similar to the answer is yes. We have just to set up the environment, in this case, create a track, so several gates, and to shape a reward such that this task and the environment are really well described. In this case, the rewards are really simple. To fly super fast through these gates, we need a progress reward. That means that at the next step, we need to be closer to the next gate. There is a gate reward. In this case, we are waiting for at the gate. The agent passes to the gate, and we give him a sandwich. We have safety reward. That means that we need to be closer to the center of the gate, and a collision penalty. In this case, we penalize the agent if it falls or it crashes on a gate. The observation, to setting up the reinforcement learning algorithm, we need an observation space. In this case, it's really simple. It's the configuration of the robot, not the absolute position, just the base height. And we need also information about the environment and the task. In this case, we need just the relative gates corners and the robot, the two next corners. So the robot knows about the next corner and then the next corner. So it can have a preview on the next target. And the action space, it's really simple. It's something that we can control. It's the joint position and the thrust. The results are this one. After our training, this is the rollout. the robot flies super fast through these gates. It doesn't move really elegantly. But here, the reward is really simple. There are few penalties, for example, there is the pose that should be close to 0, but not a lot. There is not a lot of reward engineering. After accomplishing this task, we ask to ourselves, can we use the legs? So learning to walk, learn to use the legs. In this case, there are few rollouts of policies that are really simple. I just ask the robot, move forward. Clearly, this is not enough. Clearly, this is not enough because the robot is not aware about his model, is not aware about energy consumption or whatever. We don't even know how we walk. It's a continuous falling. But what if we show the agent how we move? There is this nice work that is called adversarial motion priors that takes cue to generative adversarial architecture and also animation techniques. In this case, we can set in the environment some dataset that show kinematically how an agent moves, in this case, a humanoid. So just to explain what is an adversarial motion prior approach, we go back to generative adversarial networks. In this case, we have two networks. The first network is a generator. The generator generates data. And there is a discriminator that is able to distinguish between real data from a data set and the data that are generated. In this competitive evolution, discriminator becomes better and better to distinguish real data from fake data. And in turn, the generator is more and more better to generate data that are similar to the real data. If we translate this approach to reinforcement learning setting, we can substitute the dataset with datasets that is composed of motions, kinematically explained. And then we substitute the generator network with an RL algorithm. In this case, it's our PPO algorithm. Moreover, we can add another part that is related to the task. So we want the agent to achieve a task. If we translate this to ergoCub, at this point we don't want just to walk. We want to walk and fly. And the dataset will be composed by walking motion. In this case, I have to thank Paolo that helped me in generating this motion, and fly motion that I obtained using the multimodal trajectory optimization that I presented before. The reward, it's really simple. We don't have a lot of reward engineering. We have a style reward. Style reward aims to imitate the motion from the dataset. So walking motion on fly motion. And the goal reward depends on the task. So for example, in this case, it's really simple. Reach a target. That means go toward this target at a certain velocity. The observation space is, as before, we have the configuration of the robot. We substitute the gate corners with the waypoint position relative. And the action space is really simple, the position and thrust. But we have to add another module that is the AMP observation. In this case, these are the features that we pass to the discriminator. In particular, we pass the observation at step K and step K1, so 2 consecutive steps. And the discriminator is able to distinguish from motion from the dataset and motion from the agent, up and down. And discriminator gives a feedback to the policy. So the more it is closer to the dataset, the more the reward is high. These are the results. So in this case, the task is really simple. We have some waypoints on the floor and in the air. And the robot is able to switch seamless from walking motion to fly motion because these are in the dataset. In this other test, there is also an height map, and this height map is passed to the observation. So the robot is aware about the environment. It's not anymore a flat ground. So there are some pits, some falls. The robot, in this case, is able to understand when he needs to fly. So it doesn't fall and basically it continues on this path. A bit to show you behavior. This is another test. Really the same, but in this case, I just simulate more environments, more agents than the simple one. Conclusion. So these are basically my reflection on this work. Massive parallel simulation environments are really powerful. They can scale up really fast with respect to single agent environments. What I perceived is that to fly is really easy. To describe a task through a reward function related to fly is really easy, but to work is really hard because we deal maybe with hybrid dynamics. In this sense, we can go over hard reward engineering with generative adversarial networks. So we can give a prior to the agent and describe the behavior. So in this case, learning is really easy, and the agent can learn by showing what we want to do. This approach that contains two rewards, one related to style and one related to task, allows the robot to modify this style. So it can work in a different way from the dataset in order to achieve that task. And my question is, my reflection is, I don't know if these results could be possible using a classical control and planning technique, model-based. As a future work, I would like to insert more patterns, because for now there is just walking and flying, but maybe we can jump, running, I don't know. And we need also to fill the sim to real gap. So maybe domain randomization, inserting the jet dynamics inside. Thank you.
Thank you, Giuseppe. Any question? Yes, Gabri, aspetta.
So we talked about it already several times in the meetings, but so you said one of the future work might be sim to real gap. Yeah. So what's your feeling about this task? So do you think that the sim to real gap is very large at the moment? That with some adjustment, like adding the jet dynamics and the domain randomization is enough, and then we can test it on.
Honestly, I don't know if it is enough. We have to try on the robot, but we saw that even with model-based stuff, the sim to real gap is high. So maybe with the domain randomization, that is another approach, we can fill that gap even more. And then we have thousands of agents that can learn to deal with a lot of situations and a lot of models.
Also for the audience, if it's there, yes, Diego.
Sorry.
Quick one, Giuseppe, do you think that position-based control can create problems on sim to real?
The thing is to pass. In that case, we can domain randomize the two parameters. Yeah, they have to spot that.
Thank you.
Okay, so Stefano, you might let's thank Giuseppe again. So concerning the sim to real, Gabri's question, I think that the current work that Filippo is doing along with the previous work top of Diego's work on JAXIM might also be helpful, because we are trying to develop somehow our own massive parallel simulation infrastructures, which would allow us to insert easily second order dynamics. So this is important. Okay, so I think that actually it is fundamental for us in order to then bridge that gap, because then we can put the hands. Isaac Gym is by NVIDIA, it's closed, so it's we cannot play with it. Okay, so we move to the Stefanos and the Alpha team. Yes, Stefano, please. We are on time. By the way, today we have the social event at night and the demonstration on the robot.
Okay.
Okay, let's start. Let's move on this discussion of weather. Okay.
Okay, so well, good morning, everyone. So I'll be presenting the activities and the motivation behind the Team Alpha. So, well, first of all, motivation. Well, actually, thanks to also to ECAP Tech, we've been experienced. We have experience with different type of robots, starting from a pretty small iCub, passing through iCub 3, then up to ergoCub. And those are robots with wheels, by the way, although internally we do not have much experience with that. So the point is that we were able to scale up our algorithms, starting from a pretty small robot to a much taller one. So you can see the difference between the first robot on your left and ergoCub, so the tall white one in the middle. So the next thing is that we are definitely using the same pipeline, and we're being the more the robot was growing, the more we understood about the tools that we had and more about how to get performance out of those. So the idea is then, okay, what's next? What will be the next robot? Also for us, for understanding, for having better understanding of the field. So the mission is to develop the new generation of iCub with elements of agility. Well, I mean, we've seen the awesome videos by Giuseppe right now, so it's very cool to have similar running and jumping robustness. So the robot should be able to fold and stand up, or at least not to break too much and not explode. Some sort of intelligence, sustainability, elegance, because and standardization, so that or at least go toward the more industrialized production. So the team is small. Are the 5 people on the core people are the 5 on the left, but all in our increments, in our update meetings, we also share the room with the team Delta, and this collaboration is very important because we need to know what's currently breaking with the robot right now, what's necessary for the robot right now in order to understand how it can be better in the future. And then we have a support team on the right. Okay, then passing to what happened. So again, the team is small and we are ramping up. So we had new members joining the research increment that had let's say climbed the learning tree. And also we had the graduation of Roberto, so congrats, Roberto. Then we had what I decided to call tangent activities, so activities that weren't directly in the direction of the of Alpha, but that really took some person time. So we had a pretty big participation to demos. We have in total 14 demos in 13 weeks. Of which we had 3 DEFCON 1 and 7 DEFCON 2. Now, for those that who don't know, DEFCON is our internal classification for demos. So usually you can go for a simple visitor, a relative is visiting, your grandma is visiting, wants to see the robot walking, up to a live demo on public television. So DEFCON 1 and DEFCON 2 are the highest level and correspond usually to demos that are outside the lab. So, for example, ICRA, there has been the shooting of NOS, there has been the year of NOS, and then we had a bunch of important visitors where we had the inauguration of the CRIS, the visiting. So this all in 3 months. So it was quite a big effort from part of the team. And then we had a science paper rebuttal that is personally took a lot of time to take home. These are more or less the factors that also affected the milestones. So, for example, we have some carried over milestone. One was for me to use HipHop, this new Python library, to develop to perform a standard set of motion for a humanoid. And this was open also before. I had 2 open issue from previous increment that remain open, and then another one that has been added recently. And then we needed to finalize the step on an event terrain planning, but this actually clashed with the graduation of Roberto, so it remained more or less constant. we have a new open issue, a new closed one. Then we had another carryover milestone, but this was just we just needed to close. It was related to the activity of defining a logo. So thank you very much, Francesca, for the app, and we converge toward the logo on the right. So just the backstory is an alpha, and it starts from blur up to a simple model up to detailed model. So this is kind of the idea. Okay, then we want also to have to define a validation infrastructure for ergoCub, but this activity didn't really start, and neither the investigation of sensitivity analysis for code design and starting planning. These are all activities that got completely stuck. Then we also wanted to investigate the generation of agile motion using trajectory planning, but also this activity was blocked by previous activities. Among other activities, we wanted to investigate how to use RL for co-design. So this activity had some new open and closed issue. And starting using RL algorithms on Jaxim, and this activity is really ongoing. So all actually, Filippo did closed a lot of issues, 14 here, and one is remaining open, but it's instead for the use of Jaxim with reactive controllers, this activity didn't. There was no breakdown yet for the activity, but we're more on the learning phase. In fact, among the new milestones that we did not define during the past increment, we have get acquainted with Jaxim RL. So we both when you channel total close about 13 issues, and also apply RL to multi-joint model. So Filippo here close the entire milestone. Well, actually, the milestone is still ongoing, but an active work. And then there is a work of Carlotta that we'll present later about performing zero-order optimization. So more details. So I'll go quick through statistics. Well, for what concerns cumulative flow, we had about 88 closed issue, but this probably involves both the issues of alpha and delta that share the same board. Well, share the same repos, not the same board. Well, instead for the cumulative flow, there is a slow trend, increasing trend of issues. So we are opening, and some of we're not closing. It's also visible a bit not so much in the control chart, or you see that the standard deviation is got increased actually starting from May. It was about when we started also doing all the demos. Focus on the release report is about 52%. It is comparable to what we had on previous increment. Something definitely we need to work on. The burns down real quick also show that the amount of closed issues is not so much during various burn downs. You see that there are huge jumps that usually refers to low number of issues closed, but it's pretty much constant. Except from the last 2 weeks where we had more of an assessment phase. Okay, so this closes the presentation, and happy to see you.
Yeah, it's been a really busy period for the demo stuff. So for those who don't know, I mean, being outside involves a lot of activities. Bringing the robot to London, for instance, been incredibly tough. And also all the side activities clearly impacted the research increment. So yeah, this was somehow a big, say, shift of focus. And but fortunately, this period is gone. So now we move on. Okay, so I don't know if there is any question for Stefano, or we move on. So let's thank Stefano again, and we move to Carlotta. We are 5 minutes in advance. Showing off. I mean, what I think is that this is really dangerous. See, better to wait few minutes because people might connect only for. Yeah.
Ciao. Con la telecamera aperta senza parlare così.
Okay, Carlotta, please, the stage is yours.
Ciao. Hello everybody, I'm Carlotta, also for the people in the cloud that maybe don't know me. And I will basically deal with the Alpha Team vertical presentation about gradient-free methods for hardware optimization. So first of all, I mean, this is a work that is done in the lab, generally speaking. I'm not the only one doing it, but there are a lot of new faces, so I think it's worth doing a little bit a step back. So why hardware optimization? So why in the lab also, generally speaking, we decided to move towards this kind of subject? And first of all, these arise from the analysis done on the robotics world, generally speaking. Basically, what usually happens is that we have a hardware, we have a bunch of action that we would like the robot to perform, and then we have a so-called, let's call it behavior, that is what usually control guys and girls deal with. So basically achieving such a behavior. What usually happens in the robotic world is that the hardware is built and then given to the, let's call them the control guy, they try to do whatever they can given the hardware in order to achieve the desired behavior. This is something that basically in the years turns out to be not efficient, because basically if you would like to achieve a certain kind of behavior, you should have the hardware that follows. So what we try to do is to answer the question, which is, can the robot design in itself be intelligent? No video is starting, but we will make it start. That's enough, I think. So basically, the answer that we try to answer is, the question we try to answer is, can the robot design be intelligent? We have on the left side some models of robots that turns out to be inefficient with respect to the task they have to accomplish. Even though the video are not starting, we have, for instance, Lorenzo that tries to deal with the iCub 2.5, working on ergonomy, but for sure, Lorenzo is almost 1.80 meters tall, iCub is 1.20 meters, and with whatever he can do with the control architecture, he will always need to bend, so the ergonomy cannot be improved too much. We have the iCub free robot tries to walk. This actually was an issue, not really related to the robot, but we have an hand that starts like being removed from the robot when we were trying to walk. Another kind of example. Instead, we have the passive walker, which is a robot that in itself, with only the design, is able to walk. So is able to show an intelligent behavior only through the hardware with respect to the walking task. So the answer is yes, the hardware design in itself can be intelligent and can actually help in achieving the task. So what we try to do is optimize the hardware with respect to the task that we want to accomplish. So closing a little bit the introduction, so why we are doing this, this is the outline of the presentation. We will go through a few methods that we applied for doing co-design. Basically, we go through B-level optimization, and we show the results, and then we will go through the co-design method, co-design in itself, and the particle zero order method, that is what we are lastly starting to use. So first of all, about B-level optimization, this is a work done at the beginning of this year, where we were trying to define the ergoCub 2 robots. So we were dealing with a human-robot collaboration. So we wanted to optimize the hardware of ergoCub 2 robots for performing payload lifting task with a human. And for this purpose, we develop a B-level optimization. Basically, in the B-level optimization, we have an outer loop, which is formed by the genetic algorithm that generates different kinds of robots. We call it chromosome generation, because basically this is what you deal with when you're working with genetic algorithm. And basically, we vary the robot with respect to links length, links density, and also motor parameters. Then we have a block that for now for you should be obscure, which is about ergonomy metric computation. So we have something that allow us to evaluate the robot design. And once we have ergonomy matrix, we compute a fitness function that evaluates the ergonomy that such a design is able to achieve with a human. And then we do a population update. So basically, we evaluate the different robot designs output by the genetic algorithm via analyzing the ergonomy of interaction. How do we do this? Do we do this with an internal loop? We have then, this is why the B-level, we have then an internal loop, which is a nonlinear optimization that, given the robot, basically analyzes and optimizes the collaboration with a different kind of humans in doing a payload lifting task with different kind of loads, and then uses these different tasks that the robot given by the genetic algorithm performs to evaluate and basically to update the population, so trying to converge towards an optimum set of hardware parameters. I will go really quick about this since we do not have a lot of time, but basically this is the math behind the nonlinear optimization problem said before. So the outer loop is a genetic, give us an hardware design, and then we solve an optimization problem. Such optimization problem is basically dealing with, as I was saying before, different collaboration, payload lifting collaboration, with different humans and with different loads. It finds the best configuration of human-robot load for performing such a task. We have different constraints, the dynamics, static condition, range constraints. I will not go in details through that because I give them from Guaranteed. If you're interested, there is a paper anyhow. And, or I'm here available for any question also. And then we have, instead in the cost function, basically is what we are interested in because it's what we are trying to optimize the robot with respect to. So we have the first one, which is the energy expenditure. And here it is important to say that this energy expenditure is not only the robot one, but is the human and the robot. So we are optimizing the hardware parameters of the robot with respect also to human metrics. And is what actually in the fitness function of a genetic algorithm is taken out from the nonlinear optimization problem. Then we have a task aiming at avoiding singular configurations. This is quite important because what could happen is that if we do not add this, basically the hardware will be optimized and overfit singular configuration. What will happen could be that we have an hardware parameters that are being optimized such that the robot will be always singular, because this will be the minimum set of kind of torque in which it can collaborate with a human. But we know that singular configuration, we do not like them so much, let me say. So it's something that we should for sure avoid, that we have hardware parameter that overfits a collaboration that implies a singular configuration. And then we have another kind of task. This is the lower priority, which basically tries to minimize the difference between the different configuration found. This is such that in the future we could have also like trajectory performing, so that the sort of trajectory is implied in the optimization problem. I will go really quick through the results since I think I'm a little bit late. So this is a kind of output we are talking about. So this is what the genetic algorithm does. We have a population which is being updated. You see changes in colors because what we are changing are not only shapes. So it's something that cannot be seen in an image. So we put also a change in colors so that you have an idea. I will make it start again. And then we have the fitness that changes over time that I was saying before. The fitness is computed through a nonlinear optimization problem. We evaluated the output not only static condition, but also in a simulation. And basically what we did was comparing it with respect to the nonlinear optimization output. So one of our previous work about hardware optimization, and both in static condition and in simulation, the B-level optimization, they define a set of hardware parameters able to show a minor energy expenditure with respect to the one optimized only via nonlinear optimization. Then the co-design, basically we are starting in the last month to deal with the big dragon, let's say, about the PhD and the work we're trying to do. So basically the idea is to optimize together hardware and control parameters. And if we translate this into a pure mathematical problem, as we organize so far, this is not the only way, but basically what happens is that we have an x, and we want to find the x such that we minimize a certain function, which for us is unknown. Its derivative form is unknown. This is for now, and is done because basically what we are doing is we are using a simulator for evaluating the robot behavior with respect to different tasks. You can see here, I will go more into detail about how these things are done, why f of x is unknown, but basically for giving an idea, we have a stick bot, so our generic robot walking, and we have a fitness with respect to which we want to optimize the hardware and the control, which is the mechanical power. Then we have a payload lifting task, and we have a fitness. So basically, for doing this kind of work, we develop an architecture that exploits gradient-free methods. For us, I will be a little bit generic because both the genetic algorithm and the zero-order gradient-free methods. Then we have that basically generates a set of hardware and control parameters. And then for evaluating how those let's go with that, that robot design output and set of control parameters behave with respect to the task, we develop an infrastructure that works with MuJoCo, allowing us to go in parallel and basically to minimize the time needed for performing the evaluation of the hardware design. And then we have an MPCA, an instantaneous controller. We basically perform a simulation, perform a loop, we make the robot do stuff, and then we evaluate it with the fitness. About the inner block, so what happens is that we have a set of hardware parameters and a set of control parameters. So with the hardware parameters, we develop an infrastructure which is able to automatically generate URDF using URDF modifier. And from such URDF, it automatically generates also a MuJoCo model, which needed a little bit of tricks because MuJoCo is natively does not support floating-based system, so it's not able from a URDF model that we usually use with Gazebo to simulate a floating-based system, but we develop an infrastructure that automatically does that, so we have a robot model. Then we have a set of control parameters. Such control parameters enters to the working infrastructure, which has been parameterized with respect to such control parameters. And so then we are able to simulate the working infrastructure, given the new robot, given the new set of hardware parameters, and see how this behaves. So for optimizing, so we want to optimize control parameters, hardware parameters. We do a simulation, we compute some metrics with respect to the function, walking metrics or like payload lifting metrics. How do we optimize such vector of x? Because we know nothing in the end, we do not have derivatives, and we do not know its form at all. So basically, we started for this a collaboration with Malga, Lorenzo Rosasco, particularly the Lorenzo Rosasco group of the University of Genoa, and we are starting analyzing the use of zero-order methods for optimizing such quantities. So with X, we have links length, links densities, and the control parameters are the MPC weights and the instantaneous controller gains. And what happens is that the zero-order method, it's a particular instance of it. We call it a particle zero-order method, because basically for avoiding the problem of getting stuck in local minima, we have, for instance, 10 particles. Each particle represents an x of k, and each particle is updated independently following a zero-order method that basically approximate the gradient of a function by computing the finite difference averaging on random direction. This that you see over here, we have, for instance, also a projection on the constraints. So you can also project the x found, the new iteration found over the constraint. This is that you see in the slides is a simplified version of the algorithm. With the Malka group, we are doing also some refinements in order to be faster, in order to be more efficient, in order to be sure that we are covering all the search space, because this is something that is quite tricky when you're dealing with hardware parameters is, am I covering all the search space, which is enormous, and other stuff, but for the sake of simplicity, I put only the simplified part. And basically, we have that each particle is updated following this, and at each iteration, it's evaluated. This is good for different, we already did some analysis and it turns out to be quite faster with respect also to a genetic algorithm and to converge towards a more optimal solution. The fact that it's faster is also that it allows you to parallelize better, let me say, because the genetic algorithm has the drawback that you can parallelize over population, but not over generation. So basically, each generation must be computed sequentially. Instead, here, each particle lives by itself. So you can parallelize in different ways. And also, you can parallelize along the direction of the random direction on which you're averaging the gradient. On this, we are facing another issue, which is the motor parameters. This is a discrete ensemble, this set. Grazie. This is a discrete set, so we are not continuous anymore. And on this, we are doing some work. We are thinking about looking for the probability of a variable instead of a variable itself, or applying mixed integer methods, but we are still working on that. What we start to do is also start using the zero order method only for control gains tuning, allowing us to go to the real robot. And basically what we did was, this is any really early results that we did together also with Lorenzo, with the output of Malga. And we start comparing human guess, genetic algorithm, and zero order. First of all, let me say that we were already happy that things do not explode, which was not given for granted. Mujok is a new simulator for us, and the sim to real gap could be quite big instead if it wasn't. And also it's good to know that the human guess was not included at this stage in the initial condition of both the algorithm. So we weren't starting from that. And as you can see, all three, I mean, let's concentrate on the genetic algorithm and zero order, can do the task which was lifting a payload. If we take a look at the element of the function, so we have the sum of the joint error tracking and the sum of the center of mass tracking, we can see first that the genetic algorithm and zero order have bigger errors for the tracking of the joint and for the tracking of the center of mass. And but we can see that the zero order has a lower error for the tracking of the joints with respect to the genetic algorithm. So as I was saying before, it converges towards a more optimal solution. Let me say that it's worth underlining, we didn't introduce any weight in the function at this stage. So what happened, and we are doing other iteration, is that the contribution of the joints was eating, let me say, was completely covering the contribution of the center of mass, which is quite small with respect to the joints. And this is not good because basically we use the joints as a regularizer, because if the center of mass is not followed well, the robot falls. And this is what we don't want. So we are doing some iteration on it in order to add weights, tune weights, in order to achieve better behavior. And with respect to the human guess, we started putting it into the initial condition and to initialize in a smarter way the algorithm. And now we are finalizing the work with Malga, such that we want to draw this comparison with the genetic algorithm zero order, but we are moving towards the walking infrastructure, which is quite more complex. This finishes my presentation, and thank you.
Okay, any question? Yes, Ines.
So,
Okay, basically we are, Icotech gave us 3 different kind of motors that are already customly built, which are the so-called SML, and we make them varying by the inertia, the mass, and the torque limits. And basically the gearbox, transmission ratio, gearbox, and we are starting introducing them. We still need to actually go deeply into it. Mujoko gives you the possibility to have callbacks from the motors, and it's there that we would like to introduce them, but could be tricky somehow. And so we are still working on that in order to understand how to depict the real dynamics.
yeah, because we know that we need harmonic drives with high gear ratio, and but this has also and it's difficult. So it's nice to use parameters your problem, even because consider friction. So decide for certain power, and then it's not enough. So yeah, this would be.
We can discuss before which parameters
Okay.
close the loop could be.
Okay.
Since you're doing the
Yeah,
another
because
work.
we are talking about joint torques, but then have a friction. What we send to the motors is current.
Yeah, we can for sure. I mean, it could be useful so that we have a model that helps all of us. Grazie, Ines.
have more methodology. So I'm more familiar with systems, but also here is a data generation.
You can see it in that way sometimes,
yes,
somehow.
Evaluate, so in this case with genetic algorithms, where do you think the biggest bottleneck is in the rollout, let's call it rollout, or in the algorithm? So if you could choose, would you prefer getting a much better algorithm, or a rollout that is that can give you infinite data in 0 time?
No, the main issue, in my opinion, is in the algorithm itself. I mean, genetic algorithm is really powerful somehow, because when you have a gradient, I mean, first of all, it's easy to set up, easy to implement. We implemented our version, we use a library, it's full of libraries. And when you have a gradient free, I mean, when you do not have access to the gradient, it can be really useful. On the other part, it is not random. It's better than random. Fabio also did a lot of, we have a lot of plots by Fabio Viceconte about that. But it's not even, I mean, as the zero order has some approximation of the gradient. And sometimes it's really difficult to understand where it's going, how to deal with all the parameters, because in itself, a genetic algorithm is not simply, let's do children, because in that it's an evolutionary algorithm, but you have the crossover, the mutation, which kind of crossover, to be sure that everything is working, you're covering the search space, is quite impossible to be sure. Instead, in the zero order, you have some math in it, because also, as you were saying, you can do this with RL. This is what Filippo is doing. You have issues with the timing there, more or less evaluating the function, but that could be fit. So if you're moving towards this kind of method, in my opinion, you should have some math, some model in that, so that you are exploiting. You do not do learning, but you exploit what you know about the model. So I'm really happy about this zero order in itself, because I think that it could work quite better, and the first output starts showing it, and we will see anyhow. But on the genetic, I would say it's a good starting point for sure, but one has to keep in mind that it's not random, but is close to randomness in itself. Thank you.
Okay, I think we have to move to the next speaker. This thing is really dangerous. So let's thank Carlotta again. And now we have Giulio from the cloud. Giulio, how are you, first of all?
Così, vabbè. Okay, so I can assume that you can hear me?
Yes, nicely. So I just wanted to say that we often focus on this code design story on control parameters, other parameters. Someone has to start the perception layer. So because, you know, this is control is the dual problem of perception. So anyways, I wanted to mention this. Giulio, please, the floor is yours.
Okay, yeah. So this is the presentation for the Delta team. I'm Giulio Romualdi, for the one that doesn't know you, and I'm the Scrum Master of the Delta team. So first of all, who are the main actors of this team? So probably before starting from the people, let's start from what we try to implement. And we are mainly focused on designing a control architecture for locomotion, and the control architecture is in general composed by these 3 layers. Then before Giuseppe presented the reinforcement learning stuff that destroyed this approach. But still we are, let's say, old school for now. And then so we have a trajectory generation layer that is in charge to generate high-level command. Then we try to adjust it, and then we try to feed it on the robot. And finally, we have to close the loop with perception and estimation. So keep in mind this infrastructure, the actors are people here. So Paolo Viceconte is the main, let's say, developer for the trajectory generation. I'm the main developer from the trajectory adjustment, while I'm working with Ines for the trajectory control. And then for the perception and estimation, there is Ines, Guglielmo, and then Filippo that just arrived last week. So which is our mission? So probably you have seen some video from the robot, ergoCub, also iCub walking here and there. And so you may say, okay, you fix all the problem. But actually it's not like this, because as you can see here, the robot was still tangled with the crane. And why we are afraid of this? Because sometimes back in time the robot was falling, and also is falling also now. And when the robot fell, we break the robot in a crazy way. So the idea here is to design a new, let's say, architecture that is robust, reliable, and dynamic. Robust with respect to uncertainty due to the environment, but also uncertainty due to the low-level tracking. And we want to frame this into a new locomotion architecture. So let's go to the, let's say, the team objective. One common objective was to perform the ICRA demo with the ergoCub. And here we had two, let's say, separate tasks. The first one was to prepare the possibility to log all the data required during the demo, and this has been achieved. All the data, I think there are a lot of giga and hours of data, are now, let's say, all the members of the AMI team can use them. Then another task was try to have the central NPC plus adherent up and running during the ICRA demo, but no, we failed. Regarding the state estimation, we have a low-level part and the base estimation. For the low level, Ines was the main actor. First of all, was to test the estimator with an external contact on fixed base configuration, and Ines was able to achieve this goal. Also test the base estimator online. So right now we have this estimator that runs in the main, and not by default, but there is a possibility to run it in the main YARP robot interface. And in this case, we'll, let's say, do the same job that Whole Body Dynamics is doing, and then closing the loop with the torque control. So Ines was, she finished all the task. And this is one of the video. In this case, the leg, so Ines tried to ask for a 0 torque on the leg, and then we never seen this kind of, let's say, motion. And then in this video here, we try to, let's say, accomplish a Cartesian task. And back in time, using Whole Body Dynamics, we were not able to have the foot moving at all. While now we can, thanks to the better estimation, we were able to increase the low-level gains, and then in the end, the tracking, the overall tracking improved. Regarding the base estimation, Guglielmo finished the implementation of the base estimation algorithm that used the IMU of the stance foot. So we merged DPR. Now he's working on the testing on the robot without closing the loop with the working controller. And so the next, let's say, the next task has been delayed. This is the one related to closing the loop with the estimator. I didn't work on the porting on the Prashant base estimator on the ergoCub, and then also regarding the data quantity with the usage of the cameras. Let's say for the base estimation we delayed, but I played a bit with the camera of the robot in order to, let's say, at least for me, it was the first time that I was working with this kind of computer vision algorithm. So for me, it was a brand new stuff, even if it's not brand new. So this is a point cloud that has been generated using the data of ICRA. And then another nice thing that we developed was to sort of augmented reality, we can call it, using the real sense. So here we have let's say an algorithm, a neural network that segments object, humans, and whatever in front of the real sense. And then using the mask that can be taken from this neural network, it is possible to print let's say, the average distance of the object in front of the human, of the robot. And this is, in theory, should help let's say, the user while operating the robot. So those were the advantage of, let's say, of using vision and try to play with the vision in the Delta team. Regarding planning and control, we try to we are working actually to test the adherent with the nonlinear central MPC. Only actually there is written iCap3, but is ergoCub. And then the others has been delayed. So design on linear approximation, nothing actually, and also detect the controller with the real hardware, nothing. For the new tools, actually, Paolo did a super huge and nice literature review, and actually later will explain what he discovered about transformers regarding the trajectory generation and behavior composition. And then actually one of the tasks that I had was to get acquainted with the reinforcement learning algorithm using Isaac Jim and play with some toy problems, but nothing happened. So regarding thesis publication, Ines is actually working on, okay, here is literal paper, but then I think it will be ICRA paper for joint torque estimation, and she's writing the paper while she's doing the experiment. The paper on the adherent and the central MPC has been delayed because we are working on still on the implementation, but the deadline has to be ICRA, so we cannot escape from this. Then Paolo defended the PhD thesis, so like last time. So now Paolo is actually researcher. Yeah. So I decided to do this prize for the Researcher of the Month, given the, let's say, the effort that she already discovered. So Ines won the prize because she finished all the, let's say, all the milestone of the research internet. Okay, so now numbers. Yeah, so this is the cumulative workflow, more or less the number of, let's say, close issue and increase over time, but still we have a constant number of in progress issues during the entire period. Regarding the team statistics, more or less we have, I mean, we need 1 month in order to close one issue, because the rolling average for the last 10 issues. The average is 38 days. So I think we should improve in having smaller issues just related to the task that you want to, let's say, achieve. Because 1 month for achieving one issue, I think it's really high. Still, there are some issues that are really small, and then in 0 days, so we open it and we close them in 1 day. We should try to improve in the task breakdown activity as a team. Okay, we are able to complete 108 issues. So I divided by 4 because Filippo just arrived last week. So more or less, we closed 27 issues in this research increment. There is this plateau here that is ICRA, and so probably in this period, the robot was not available also for some experiments. There is this plateau here that I don't know what is this. And this plateau here was COVID. So after ICRA, we came back with COVID. I think a lot of people from the lab. Okay, the burn downs report. There are some nice, bad burn downs. So for instance, during this second sprint, it seems that nothing happened. Yeah, I think that we should try to, well, I go also on the next one, but more or less they are similar. We should try to improve in having the issue, only the issue that we are working on the, say on the sprint, because I'm assuming here that there are issues that are there, but of course we cannot do miracles, so we cannot work on 10,000 stuff together, and so we should move them from the sprint if you are not working or planning to work on them during the, let's say, the burn during the sprint. Yeah, so they are more or less similar, all of them. The latest one is actually still active. Here we are doing nice. Let's see which one we are finishing it. Okay, so that's close the presentation. The next one is will be Paolo presenting the transformers for trajectory generation. If you have any questions, please speak.
Okay, any question from the audience? And meanwhile, Paolo comes. No, thanks a lot, Giulio. What does the researcher of the increment win?
Ah, no, yeah, she finished the task.
Like reviewing a pull request. So.
Oh, but now, okay.
we should actually, it wins. Kidding. Okay, let's thank Giulio again. We move to the next one. Paolo. These things are really, I'm going to complain with the gatti. Okay, Paolo, please talk closely. Yes, thank you.
Okay, thank you. So, hi everyone, I'm Paolo Viceconte for the cloud. And yeah, welcome to this vertical presentation of the Delta team, which is gonna be a little different from the previous ones, since we are, I'm not going to present some results or intermediate results about our own work, but it is more something like sharing some knowledge about new directions that we are basically trying to investigate. So in particular me, but also Carlos, as Daniel was mentioning before, we are basically aiming to autonomous, let's say, behavior generation based on multimodal data. And one way to do this is by using transformers. So today I will give you a brief introduction about this neural network architecture, which gained a lot of popularity recently. So to do so, I will go through some motivation. Then I will introduce the architecture itself and explain how it has been successfully trained in the literature, with a special emphasis on the diversity of inputs that this kind of architecture can handle. And finally, discussion will conclude the presentation. So let's start from motivation. And as regards motivation, I will let basically a transformer speak by itself, with the only constraint of being, let's say, as concise as possible because of our time limitations. And yeah, as a transformer appears to know, the main reason behind being interested in this kind of architecture is their excellent capability at modeling sequential data due to the attention mechanism. And as you can see here, this is particularly successful for natural language processing, but this is not the only context. Indeed, if we switch to vision, for instance, transformers have been shown to excel at generating captions for images, but also generating images from captions, as you see here. But this is still kind of far from what we are used to work on. So if we ask back to our transformer friends, and sorry about that, but it was too tempting, I couldn't resist, we can kind of agree with it that the key feature of transformers to basically excel at modeling sequential data is crucial also in most of the robotics related tasks. And indeed, transformers have been successfully used for manipulation, complex and also sequential manipulation, and recently also for humanoid locomotion. You can see here successful locomotion over different terrains, but also, oops, but also under different disturbances, let's say. And these reasons were basically enough to get our attention and to motivate us to investigate this new architecture and try to exploit it for our purposes. But what is actually a transformer? So as illustrated in the original paper in 2017, which by the way has a kind of incomplete title, a transformer is a neural network architecture based on the mechanism of attention as an alternative to recursion or convolution. So basically, the main claim here is that transformers can deal with sequential modeling just using attention, and this is how, in the title, they say they mean that attention is all you need. So it's enough to model sequential data. Something about attention. You can think of attention in terms of relevance. So for instance, here you have two sentences, and you can see how the word it in the right side sentence attends mostly to the animal on the top, which indeed semantically, like in the sentence, it refers to the animal, but also, for instance, it attends significantly in the bottom of the left column to the word to, because it was to, like it and to are related by the verb in the middle. So attention is basically relevance. How does this translate mathematically? So if we have a certain number of tokens, in this case words, but they could be different objects, and we assume to express them in a matrix X, and we also assume to have some way to convert this X into queries, keys, and values, which can be like some kind of function learned or not. Then the basic attention operation is this one. So if you associate a query to each word and a key to all the other words, there is a dot product that basically computes a compatibility score between each word and the others. So how the other words are relevant with respect to the one we are considering, which then normalized and converted into some probabilistic weights becomes the weight for the values. So you can think of the output of this operation, attention operation, as the orange links in the figure. So how much each other token is relevant for the token we are considering. So this is the building block of transformers, but actually in transformer architectures, there are multi-head attention layers. So this block is repeated h times, where h stands for head. And actually, also the multi-head attention block is just one part of the entire architecture. It is the core component, but then there are a lot of additional layers. If you look at this, which is the original transformer architecture, you can divide it into an encoder, which is basically which encodes the input, and a decoder, which is used autoregressively to basically generate the output using the previous part of the output that it has generated before. And of course, there are many variants. This is just an overview of the simplest kind of transformer architecture. So we can proceed with useful strategies that have been adopted to train this kind of networks. So one way to do that, which is pretty famous, is the splitting the training into a generative pre-training. So you have a huge corpus of unlabeled tokens, and you want to maximize the likelihood of one token given the k previous tokens, which are where k is the length of the history that the transformer can see, and it is a parameter that can be tuned. And then a supervised fine-tuning phase, in which you have instead a labeled dataset, so some tokens associated with labels, and then you want to maximize the likelihood of the label associated with tokens. This has one good side, let's say, and it is that the transformer learns a kind of universal representation. So this can then be easily adapted to different tasks. But on the other side, to do so, you need a huge data set. So this is quite common in the context of language processing, also vision, but it's not that common to have in robotics. On the other side, transformer architectures have also been used for reinforcement learning. So here you have the usual reinforcement learning setup, but the transformer, which is used as a neural network, receives an history of the observation and actions serialized. This, of course, solves somehow the problem of retrieving a huge data set for training. But on the other side, of course, it introduces into the picture again usual, let's say, issues related to RL. Then a few words on the diversity of inputs that this kind of architecture can basically handle, because this is one of the core points, especially for our, let's say, application. And so what happens? When something enters a transformer, of course, it has to be converted into a vector. So if we start with words, for instance, these words are first embedded, which basically means being transported, mapped into a vector space in which semantic similarity of words corresponds to closeness in terms of distance of that vector space between the embedding vectors. But this is just part of the conversion, because the transformer is not recursive. So it basically needs not to handle words as a bag of words. It needs some information about the position of words in the input sentence. And this is conveyed by some positional encoding, which also can be like implemented by a function, periodic functions like these ones, or also learned by itself. So these two components are usually summed, and you have an embedding of words, which includes both the information of the word and information of its position in the input sequence. What happens instead with images? So just to mention a different kind of input. With images, usually, images are divided into patches, and each patch is tokenized. So again, it's transformed into vectors. For instance, by means of ResNet architecture, let's say some alternative ways of transforming patches into vectors. And also here, an important component is to convey also the information about the position of the patch into the image. So again, these are summed and then given as input to transformers. This is just a few hints about how transformers can handle pretty different kind of inputs. So text, images, continuous actions, discrete actions. For instance, here in this paper by work by DeepMind, all these inputs are, let's say, tokenized, so converted into vectors in different ways, and then stacked sequentially as inputs for the architecture. So as regards our possible applications with transformers, we know that transformers excel at modeling sequential data, although there is an issue with the inference efficiency, especially when exteroception is involved. Then we can say that, okay, the key features of this architecture is just attention, which revolutionized the way of dealing with sequential data, but also this is kind of challenging for very long sequences. Then we talked about different ways of training transformers. So we have pre-training plus fine-tuning or reinforcement learning. And in order to decide which approach to take, we could keep in mind that basically these architectures are likely to overfit on datasets which are not big enough. And finally, we have seen the flexibility of these architectures to diverse input sources, but also here, let's keep in mind that tokenization and embedding are crucial. So what we can do, you have seen the videos by Giulio in the previous presentation about ICRA data. What we are planning to do together with Carlos is basically to try to use those data, so exteroception and perception together to generate autonomous behaviors. And this concludes the presentation. Thanks.
Very nice. So any question from the audience, also online? Applauses, but no question. Yes, Dario.
I'm not an expert in robotics or AI, but in time series I have a little bit of experience. So it seems to me that Transformer deals really well with things that are not really linked in time. I mean, words are not a number that one makes sense after another. It's the intrinsic meaning of a word that makes sense with one another. And in robotics, I guess that you are more likely to work with time series in which one number makes sense with the other one in terms of its amplitude, basically its frequency and the signal. So I don't know, it's just an observation. Do you think that the power of transformers applied in other domains is just because of its huge infrastructure, or the intrinsic way of how the transformers work can really overcome challenges that other methods cannot solve? I don't know if I was clear.
Yeah, I agree with you. Regarding about the difference between data which are like words linked semantically with respect to data which are linked actually because of the time at which they are received. Regarding transformers, for the applications that I've been I found in the literature in robotics, it seemed that of course the size of the model is fundamental. For instance, the Gatto paper, the one who uses all the different kind of inputs, according not to the authors, but according to another paper which makes evaluation, and that takes an inference time of more than 1 second, because it has 1 billion parameters. And if they reduce the size, the performances change a lot. So of course the dimension is important, but I guess that the key is in the attention mechanism. We saw it for words, but also for data that are linked in time. I guess that attention helps to make sense only of the relevant portion of the history of data that you receive. So it still can be crucial in, even if it's not a semantic link, but a time link. I think that attention should be crucial. But I mean, we are willing to investigate that. Yeah.
I have one question. Okay.
Giulio,
Can
I give you the speech. Just 1 second. I just want to complement what Paolo was saying. That there is Giulio and Mohamed. So what I wanted to say is that motions also, in my opinion, have intrinsic meanings. I mean, I don't do like this here. I do like this here because I want to go inside the room. So somehow trajectories, when you step out, okay, a bigger level, they have meanings. Like they have meanings like words. We often talks about this with Paolo and Carlo. So the semantics of motions, okay, at a bigger level are there. You see what I mean? So motions are not somehow pure sequential time data for robots. Okay, they are in an agent that does something, okay, for an objective. So there is a semantic there. This is what I wanted to say. Yeah, Giulio, if you want to also share your, so we see you while you.
Yes. So, okay, from the no, I was wondering because at a certain point you said in order to train these GPT networks, you need a lot of data. So I was wondering the time that you need also for training, more or less. So days, months,
Okay.
hours.
Yeah, regarding the time specifically, I cannot answer because most of these papers are some of reports, others are, I mean, they don't give details about the timing, and of course it depends also a lot of on the architecture. But regarding the size of the data, for instance, the paper which uses manipulators for grasping and moving objects, they collected data with real data with 17 robots in a kitchen environment, they say for several months. So it's like a huge, really huge data sets, because you need to think that, for instance, for the transformers trained on language, data sets are like English Wikipedia. So for text, for images, also nowadays there are like very extremely huge data sets. And so also in robotics, they try to mimic some web scale data set, which is currently not available. So part of the contribution of these works is also the data set. For instance, the manipulation one, they released it and it was like part of the contribution of the work. So yeah, huge data sets. That's why maybe addressing the problem with reinforcement learning like could allow us to overcome this issue. But on the other side, if you want to use perception, then you need to simulate it in a good way. So yeah, it depends on the application. Yeah.
Okay, thank you.
Very thank you for the night. Have you given any thought? How are you going?
Nice question. Okay, so first of all, investigate better which kind of data we have from either, decide what to use and so on. We showed in the presentation, I showed the embedding for words, which is now kind of a common practice. But it's important to say that usually those embeddings are learned also. Also that part can be learned. So especially for data which are hard for us to associate to a meaning, I would say that we can try to learn some embeddings and then visualize maybe clusterizing data in different sub-trajectories and check if they are distant enough in the embedding space. So not a strategy that we decide, but possibly learn also that part.
Question? Okay, so thank you very much, Paolo, for this very nice presentation. And we have to shrink the break, so we have to get back at 11:30 for the next presentation. So.
Oh! No, io non potevo. Non c'è musica, ci volevo quello di Balsini. Bravo Lallo! Adesso anche qua non si sente. Vabbè, qua dicono complimenti, devo fare il doppiaggio. Lorenzo Rapetti. Congratulations!
Okay, so guys, it's better to restart.
Okay.
Because yes. So please. Okay, so we restarted the morning session. This is Mohamed with the update on Tau team. Mohamed, the stage is yours.
Thank you. So, hi everyone. I am Mohamed Elobaid. For those who don't know me, I will be presenting the Tau. Okay. So our team is combat. So we have Ehsan and the usual suspects as usual. Stefan. And then of course we have the mission is to maintain and carry out development activities on the avatar teleoperation. This is related to two big objectives, which are the teleexistence research axis and then technology transfer projects specifically related to the avatar. So we have several collaborations. Okay. A brief on what happened, the main things that happened in the past research increment. So as you saw, ergoCub was at ITRA, then ergoCub was teleoperated from Tokyo. Then internally we had an updated Proto 3 robot, URDF, and we started development activity. Proto 3 is a robot by. So concerning what happened, of course, Stefano mentioned earlier that we were involved in a lot of demos in research increments, but one particular demo to highlight is this one, which frankly, when we were starting testing there, is that we were not considering it as a DEFCON 1 or something like this, but it turns out to be actual review to check the feasibility of the teleoperation, at least from the side of Honda, and they were quite pleased. So that was a very nice experience for us. Also, we get to test their platforms in this visit and to define control interfaces to use our software with their okay. One of the planned milestones was to restructure the Gazebo YAR plugins and to add more, to be able to add more hands easily, especially when it comes to coupling laws. We did the coupling laws for the hand of the Proto 3 and we were able to teleoperate it, but the whole restructuring of the Gazebo YAR plugins was delayed due to activities of the day. Concerning another planned milestone, which is the collaboration discussed by Danny earlier, we started, we actually showed some results and we are progressing on that direction. We had a milestone concerning the investigation of compression of visual and audio feedback, and Stefano here did a lot of work and a lot of tests, and how we have the command that you can change codecs and various configurations, and of course we need to do some testing the actual robot height. Then for what concerns Ehsan, had two big milestones. One is to finalize the design of the new thing. He was able to use the new gloves, the VR gloves, and he will speak about this work in the also adding several features to it. Yes. Also, Ehsan graduated, so congratulations, Ehsan. I'll move quickly to the statistics. So this is a comparison. This is the most understandable part of the statistics for me. So we have the control chart for the previous milestone, which we started actually at the last month of the milestone of the research increment. Sorry, and research increment we closed 4 issues compared to the previous one, but we had longer time to get better at this. This is actually to opening issues and specific sprint and not loading them on that sprint. Able to focus more on specific. For what concerns the control chart itself, towards May and June, you can see that it's open due to famous, but then the cumulative So also seems quite normal. The in-progress issues seems to be still. We are closing some during May due to the demos, but then for what concerns the release report, we are at 57%, which was actually better than the previous research increment. The research increment around 36, if I we need to get better. For what concerns the burn down, we are not able to track the velocity, the velocity quite well in most of the sprints, especially in the sprints that are in May and June. Yep. Thanks for this.
Any question for Mohamed? It was really cool, Mohamed, to see, and all the guys who left for Tokyo to see the Tokyo Genoa teleoperation. It was really amazing. Okay, so the teleoperation demo was great. So thank you very much for all the effort. So let's thank Mohamed again, and we pass to the Ehsan. In the meanwhile, I probably had to deal with the
Okay, hello everyone. I'm Ehsan, a member of the team TAL, descended from the formerly known TAL existence team. Today I'm going to present my project on related to hand motion retargeting for teleoperated grasping tasks. So first, let's start by motivation behind this study. So imagine a humanoid robot in a disastrous situation. So in those situations, it's very difficult and dangerous to send a human to perform. So what we do, we can send a humanoid robot. So now imagine this humanoid robot needs to, for example, imagine there's a fire in a building and a valve needs to be turned off. So the humanoid robot needs to interact with that environment, with that valve. So our solution is to see how we're going to manipulate the humanoid robot hand. So as you can see, we are going to answer the question of targeting the motion of the human operator to a humanoid robot. So here's the outline of this presentation. First, I'm briefly introduce you to the technology that makes this happen. And then the background, we're going to see some background to understand the methods. And then finally, we're going to see the rest of the video as our result. And, at the end, with addressing some future works, we're going to conclude the presentation. So let's start by introducing the avatar system. As you can see, we have a human operator on the right side, on your left side actually, and a humanoid robot on a remote, distant environment. So the human operator wants to control the humanoid robot in a remote environment. And it needs to know that environment, it needs to interact with that environment, and by benefiting from haptic interface, it can better understand the remote environment without actually being there. So this means that the operator is being coexisted to that remote environment. So as introduced earlier, we want to see how we're going to retarget the human hand motion into a humanoid robot. So mainly there are two methods to do this. First, using the vision-based system, and then the other one is to use the wearable devices. The limitation with the vision-based system is that first, there are no haptic feedback. It's very crucial in a avatar system experience because we want to interact with that environment. So we get some information from that environment. And the other one is that the setup is kind of bulky, means that there's always the need for cameras to humanoid to the human operator. On the other side, we have the wearable devices, which obviously they have the haptic feedback, which makes it very easy to use. So before showing the devices we have, the first step in motion retargeting is to model the human hand. So as you can see, this is how we model the human hand. Every finger has 4 joints, middle, proximal, and abduction. But I have to say that for some limitations at this study, we remove the abduction joints for now. We're going to address in the future work. And the second step to know the robot's hands model is that we should know what we are retargeting the motion of the human. So this is the humanoid robot, as you all know, it's the ergoCub, and the hand of the ergoCub, which has 16 degrees of freedom. And the one thing to note that the ring and pinky fingers of this humanoid robot are coupled. So the first setup, the first device that we had in our lab is called Sense Glove. As you can see, it's kind of an exoskeleton. It has force feedback, vibration feedback, but it has its own limitations. First, as you can see in the video, there's always a need for the second person to wear the gloves, which is not pleasant, and uses a cable communication, which is an unpleasant coexistence or avatar experience. So we moved to another type of glove called Vert Touch Diver glove. It's thimble-based. It also has force and vibration feedbacks, plus it has temperature and texture feedback. And of course, it uses wireless communication. But there's a big challenge with these types of gloves. And it doesn't give you the joint values. So we had to see how can we overcome this challenge. So we take a look into what information this glove gives to us. So let's see what types of sensor this glove has. So first, there's an infrared sensor in the thimble, in the tip of the thimble, which basically gives you the distance information between 2 points. These 2 points in our case is being the fingertip and the palm. And then also there is a 60OF inertial measurement unit, the IMUs, which generates gives you the accelerometer and the gyroscope information. But in this study, first we are going to focus on just the distance information. So let's see how we can process those data. So it turns out that using the distance information, we can generate the values. So the method is called finger as a manipulation approach. So here we considered a human finger as a 3R planar manipulator. And basically, we're going to solve an inverse kinematic problem to generate those finger joint values, but with just using the distance information. And we're going to solve this problem, this IK problem, using the QP optimization problem. The reason why we use that is that implementation with QP is easy. We have the infrastructure in our lab also, and it can handle multiple tasks. So you can pass the tasks as equality or inequality constraints. So let's see an overview of our QP optimization of our problem. This is the overview that we have distance task and with other tasks, as you can see. Let's see what are those tasks. So first we have, as just discussed, we have the distance task, which, as you can see, there are 3 distance tasks, each for every finger of the human. But there are 3 because the gloves have 3 thimbles. And then we have a joint regularization tasks, which basically minimize the error between the desired and measured joint values. And so it prevents the controller from providing large joint values. Then we have joint limit task, we have this task because we want the generated joint velocity to be within the joint limit range of the robot. Finally, we have the SE3 tasks, also called Cartesian task. This task is here because imagine the robot is walking, all the frames attached to the body of the robot is moving. So we are interested to track a specific link frame. And in our case is the palm frame. So we have this task to do that. This is the result. This vector is the result of our algorithm. It generates finger joint values as shown in this slide. So there is another problem, as you note that we have only 3 symbols of the glove, but the human hand has 5 fingers. So we need to find a way to expand those information to the full hand. So we came up with the mask matrix, and as on the robot, we also coupled the pinky and the ring fingers with the middle one. So they act accordingly. So let's see some results. First, here the human operator is trying to do grasping action. And this is the full validation of our method. So this task was initially one of the an Avatar X Prize competition tasks. So the human operator is trying to solve a puzzle with the ergoCub. Later, yeah, in fact, it's me. We also faced a limitation here. We faced it was a mechanical one of the fingers of the robot, but this shows that how robust our method was. That in spite of that, operator could. So for the future work, we are right now trying to exploit accelerometer and gyroscope sensory data to have a better result to enhance our performance. And the idea is to, if we think that learning-based methods can be used, like by leveraging the developed methods as ground truth for training models. And finally, we can incorporate the concept of synergy to have the realistic motion retargeting. So thank you for your attention.
Any question for Ehsan? Nice videos, nice demonstration. Ehsan, can you get back to the video where you were when the human operator? Yes.
This one?
Yeah. Can you play it back?
Okay.
So I think that here the fact that the wrist is really rigid somehow it increases the overall problems of the system. So I don't know if you know, but I have been asked recently to add an FT sensor here. Okay, so theoretically we might then do the torque control of the wrist so that we get a little bit of compliance. And this is also nice because it is a kinematically closed structure. So probably we need to. Okay, so if there is no other question, we move on. Let's thank Ehsan again. And now it's time go to the lunch, as Renzi would. No, I'm kidding. For Italians, there is this really nice video that Renzi said, now it's time to go to the lunch.
We're sharing from the I share from the laptop.
No, di solito funziona molto bene con questo. Ce l'hai? Tu non c'è l'Accademia, è vero? Ok. Tu registra tutto. Okay, so I think that we are about to get there. So yes. Let's give floor to Lorenzo.
Okay, I think it's sharing the screen. Okay. So for those that doesn't know me, I'm Lorenzo Rapetti, and I will be presenting the planned and achieved objectives for the ergoCub team. So just a brief overview of the presentation. I will start with the team. Then I will give a short introduction about the project for the new people. Then I will be presenting the milestone and finally the statistics. So concerning the team, so here we have somehow the core team involved in the ergoCub project. As you may see, some of the people are also involved in other teams, so they're shared between for some shared activities. Then we have also Antonella and Lorenzo that you don't see them often here, but because they're working at Enel in Rome, so at the lab of Enel. And then we have a strict collaboration with the iFeel team. So Gianluca and Dario, they're involved on a lot of the activity of the ergoCub team. So concerning the project, so we are calling this team ergoCub team since the main focus is on the so-called ergoCub project, which is a collaboration project between IIT and Enel, in which is involved our research line, and also the HSP research line and the iCap Tech facility. So the project started in 2021, and we are getting closer to the end of the project, which is supposed to last 3 years. The main objective of the project concerned the application of ambient intelligence and collaborative robotics for risk prevention in work environment, accordingly to the objective of Enel itself. And we draft a map of the activity which are involved in the project. So we define at the beginning certain scenario, we identify certain application scenario, and then the objective is to move towards, now that we are getting closer to the end of the project, towards a validation of those scenarios, which involves both robots and wearable technologies. In order to do so, our team is involved in a certain number of tasks, touching almost all of the tasks of the project. So at the center, we have the algorithms for perception, so human perception. Then we have a task concerning the evaluation of the biomechanical risk and biomechanical condition of workers. Then we have navigation and planning for the robots and robot control. Then, besides the focus on algorithms, we are also working on some support activity, which involve the development of hardware. So we work together with iFeel for the developing of wearable technologies, and together with the iCap Tech facility for the development of new robots. And moreover, we clearly work on modeling and simulation for all of the activity. Finally, there is an additional task which concerns the usability, acceptability, and social impact of the technologies we are developing, with the view of having the technology actually usable in a real scenario. So moving on to the milestone. So we go through the milestone we defined at the last research increments. So the first part concerns the estimation or human estimation. So all the algorithm for estimating the state of the workers in the case, in the specific case of the. So the first milestone concerns the implementation of learning base for kinematics. The objective here is to achieve virtual tracking to compensate for the information that we struggle to retrieve from the wearable sensors. So on this, we move on, and we have some preliminary results. So the activity concerns the collection of data sets with multimodal sensing, so both the wearable suit and Vive tracking technologies. And the idea is then to develop learning-based algorithm to virtual tracking of the end effector of the subject during a certain number of motion. So those are some preliminary results showing the basically the ground truth measurement of the tracker. Here, the two couple of frames, the ground truth measurements and the estimated. Then we wanted to validate this virtual tracking into teleoperation scenario, but we are still missing some pieces to move towards the online usage of those algorithms. Then one of the milestones we didn't start was to somehow integrate the motion prediction pipeline to, again, try to help the kinematic estimation of human, the inverse kinematics we're using to the state of the human trackers. And instead, concerning human model, we also wanted to move towards data-driven human model. So we have some scalable anthropometric model, but still we need to integrate the part concerning data-driven model generation. Then again, concerning estimation, in particular focusing on the estimation of muscles, we validated the estimation of muscle forces with adding additional muscles in the model. So for a while we have been working just on the lower legs. So yeah, lower leg and the ankle muscles. We recently developed some new model with increasing the number of models. So here you see the back and the front of the subject, and each of the red line represent one of the main musculoskeletal muscle we are interested in. Starting from this, the next step, which we didn't start, was to have some identification algorithm for the muscle parameters, and also comparing the estimation that we do with our system with the BTS system that is available at the lab in Rome, I was mentioning. Then concerning control, so Mohamed has been working on a new adaptive controller based again on centroidal MPC with robustness guarantees, and this was, I mean, he moved on with this research, and he was able to test it in simulation, in this case with the iCap 3 model, and then the next step is the next milestone concerns testing this with the real robot and submitting. Then we, again, with this activity didn't take off, so the design of shared payload collaborative working controller. So we want to not only being able to carry a payload, but doing it in collaboration with humans. On this activity, we didn't close any issue, but we are still in the process of testing the new controller for a collaborative controller, which has been moved to Python. And we also started doing some experiment with the collaborative lifting with ergoCub. So this is still in progress. Then concerning motion generation, so this will be mainly presented in the next vertical presentation. But basically, so what we did was to, okay, the percentage here are a bit strange, since in one case we didn't close any issue, but the activity is in progress, while in the other case there was not yet a task breakdown. So this is why the 0.1%. But I mean, the activity at the end is in progress and will be presented. Then concerning the robot itself, we are working on somehow validating and comparing the ergoCub robot with respect to the ECAB3 robot. So for this, we are doing trying to setting up different experiments. I just show one of those, which was somehow nice, which was a comparison between the ECAB3 robot, so the one that is now used for IronCub, compared with respect to the ergoCub robot during walking. So in this case, we were basically sending the same command to the two robots, which were controlled on the same network. Yeah, then I'm not sure if we have the. Yes, this is like stream the video just. But yeah, it was somehow cool to set up this kind of experiment. Okay, next, so we try to increase the number of tasks we're considering in the genetic algorithm for control and design optimization. So, okay, this was presented already a bit from Carlotta, but in this case, we are just showing that one of the tasks we are going to consider concerns locomotion. And this is a video showing ergoCub robot working in Joko, which enables somehow parallelizing all the genetic algorithm infrastructure. So, I mean, we didn't start preparing a paper on this activity, even if it's an activity per se is in progress. Then we are also somehow doing some support task with iCab Tech, which is developing new ergoCub robot design. On these, we also in this case, we don't have a clear task breakdown, since we're just doing some support activity while they ask us. So what we did was to analyze some possible configuration that they are proposing, which with scaled arms for the robots, and doing some simulation tests. So in this case, the body is the same one of ergoCub, but we have different inertias and length for the arms. Then we have the performance zero order optimization for co-design, which is basically the task that was presented also within the Tau presentation, the Alpha presentation. Then finally, we have some general milestones for the project. So we finalized this activity for the questionnaire. We also, last week, we also collected some preliminary results from Ipsos, and we hope to be able to present the full study at the next research increment. Then the ethical committee submission was approved, the one concerning the ergoCub project experiments. We also have been working on setting up the lab in Rome, in Monteporzio. So in this case, we opened some new task since we are trying to finalize it somehow during the summer. With the lab is being prepared. It was we are given with the spaces. We define how to organize the spaces, and we gather all the instrumentation. And then finally, we also have, I don't know if everyone is aware, but we have also an additional space here at Chris at the first floor. So this area is supposed to be used for ergoCub and iFeel, let's say, for all the kind of experimental activities. So now the space is ready, we can start using it. So in case any suggestion on how to use, or if anyone wants to use it, discuss it. Then I don't know if someone will move there, since we have no more space. Then concerning the milestone, we in the last research increment, which was the 13, we closed 15 milestone, and that research increment, during that research increment, we also had the review meeting, which pushed a bit the activities. While for the last research increment, we had a few demos we were involved, so the number of close milestone is quite small compared to the trend we were getting during the last research increment. Then concerning the submission, we submitted 2 works in the last research increment, which has been rejected, so we are going to resubmit it. We are basically submitting them again during those days. Finally, I'm a bit short in time. So the cumulative workflow, so this is the one from the last research increment, and the new one. In the central area, I see it's a bit flat. I don't know if it's due to, again, demos or something else. Moving on to the control chart. This, again, is the last one, in which we have more than 300 closed issue, while here there are about 100. So this number somehow decreased. This reflects also what was observed for the milestones. Again, the release report somehow showed the same structure of the cumulative flow. And then we have the breakdown reports for sprints of this. Okay, so I want to thank all. I don't know if there are questions.
Yes, so I just want to mention that we, with Lorenzo, Enrico, Gianmarco, Francesco, we're running this acceptability test with Ipsos, and also Italian one, see Pagnoncelli sometimes. But it's this large company making polls, and it's really interesting that to see how they can measure the user emotions while somehow seeing robots and seeing wearables. So there are really nice pictures that then we started looking at, and they're producing it. Probably we show the next increment.
Once we have all
the data. It's really interesting to see that people, oh wow, or not. Anyways, and there are preliminary data that show that people working in the healthcare system, when they see the robot helping patients, they get angry. So they think that the robot can steal their jobs. So it's really nice. Okay, so all this stuff we're doing with psychologists in the end. So if there is no question, let's thank Lorenzo again. We move to Evelyn. Yeah. So before I was thinking, I don't know if Giulio is connected, but sometimes something I want to say, that we say that with Giuseppe that the control theory is dead and all these kind of things. With the reinforcement learning. But what I think is that actually is a way to fuse together trajectory generation and trajectory adjustment. So you can see that block together. So, okay, so please, Evelyn, the floor is yours. So it should be already.
It finally goes.
This should be already working. And probably you can just, if you can connect also the Teams call, so that you can also activate your camera and people can see you. So they engage a little bit more.
But we can actually see the screen already.
Okay, but now you see also Evelyn, I guess.
No, but I can see Evelyn and the screen. I don't know how. Oh, yeah. Okay, as you wish.
Okay.
Not morning, afternoon to everybody. I'm Evie. For those of you who don't know, I am a PhD student here. I started in January, and today I'm going to be presenting project, which is modular trajectory. So this is a pipeline that Danny showed in another presentation. This is just an overview of kind of all of the different steps that we do in the lab in order to generate control algorithms that allow the robot to do the things we want to do. And this is just to show that the particular part that I work on is trajectory optimization. And my project builds off of the Adherent framework, which is a project developed by Paolo and the others. And essentially, Adherent generates trajectories, and the goal is for the trajectories to be human-like, because having human-like trajectories means that the robot moves somewhat smoothly, and that if it were to be working in collaborative situations, it would be intuitive for the human to understand what the robot wants to do. So here you can. I wanted to pause it. All right, we'll wait for it to come back. So what I wanted to show is that the way it works is that we train a neural network called a mode adaptive neural network, and essentially we predict the next time step of some different information about the robot state at a given time, which I'll get to in the next slide. But here you see that we can specify using like a joystick controller the motion direction and the facing direction. And the robot, essentially what the trajectory generation does is that it takes whatever it predicted from the output of the neural network, and it kind of blends that with the desired movements that the user has inputted. And this blended value goes back in as input for the next time step to the network. And this is how we're able to generate these kind of smooth transitions, for example, between different directions of walking, like you see here. So here's some of the overview of the math that's involved with that project. We have a vector of input features that go into the mode adaptive neural network, outputs the same features kind of at the next time step. And these features are essentially the joint state information and the ground projection of a few different values, like the base position, the facing direction, and the linear velocity. And yeah, as you can see, the output features are essentially the same, but predicted for like the future. And for training it right now, we're using pretty typical methods. We're using mean squared error loss and gradient descent parameters. But that's not really what I focus on. So. Okay, so to motivate my project, I'll talk a little bit about what the current limitations are of the original Adherent framework. One is that the training features are really specific to just locomotion and specifically just different directions of walking. And so to that end, my work, part of what I do is to increase the modularity of this supervised learning technique such that we can have the possibility of extending it to more capabilities beyond what it already can do. The second thing is the fact that the training features right now are not very intuitive. Actually, the original mode adaptive neural network paper was for that we based this project off of was for the computer graphics field. So the most important thing in that field is for it to look good. But for robotics, we also care a lot about how smoothly it moves, not just how it looks. So another thing I did is to change which training features are used in order for them better adapted. And finally, one of the limitations as well of the adherent framework is that we had to use, essentially manual drift correction, like not a very sophisticated method, but had to, for example, set the roll and pitch orientation equal to 0 at each time step to avoid this drift. And we had to also use kinematically feasible constraints in order to reduce drift in the linear direction. And so it works, but it also limits what we can do. So one of the things that I did was also to add a control theory-based method of drift. So that brings me to my actual contributions thus far. First, I changed the training. And so the original adherent used mostly position-based information. I have kind of shifted towards more velocity-based information. So as you can see, I got rid of the position and facing direction and stuff, and I instead now use velocities. So the linear and angular velocity information, the joint state is still there as it was before. So using the angular velocity in addition to linear velocity is helpful because, again, we would like to be able to control the robot in a way that makes sense for robots rather than computer graphics. And the other thing that I did is to add the third dimension, because originally all of these parameters were ground projections. So now I have the velocity information in the X, Y, and Z directions. And this allows more modularity and will allow us to extend to capabilities and tasks beyond what we already have. And actually, as you can see, even though we have fewer different types of training features, the size of the parameters is not that different from what it was before, so the training time is. Okay, so then in order to get rid of drift, we use linear and rotational PIDs, and this is something that I struggled with for a couple of months, so it's probably hopefully useful for other people as well to talk about. And here's the equations I used. Not really PID, I guess it's more PI controllers, because we've got the proportional and terms. And essentially what is done is that whatever we get out of the neural network, so the output of the neural network, which is this predicted value here, is corrected using whatever the user wants the robot to do. So the user will use the two joysticks that are on the controller, and one of those will tell us what position we want to go to, and the other will tell us what range we want to have. We calculate an error, and whatever is outputted from these PI equations is then fed back into the neural network in order to hopefully the closer to the values that we want in order to get to the position. And then actually also the angular velocity that's outputted by the controller is used to update the base orientation. So in summary, what did I do so far? First thing is that I changed the feature vectors such that we now include angular velocity and also the third dimension of the velocity, all of them. I also kind of switched the paradigm towards velocity-based trajectory generation, which, yeah, it allows smoother motion. It's variant, and also use these PI equations in order to eliminate the linear and angular drift in, let's say, a more sophisticated way than was used before. Okay, so here of what the robot with the trajectory generator can do. Place. If it doesn't, I'll just play it on my computer. So here you can see on the left-hand side is before implementing the PIDs. So you can see, especially in the orientation, like the roll and pitch directions, you can see that the robot really starts to drift a lot. Drifts so much that it can't walk anymore. Whereas on the right-hand side, you see what things look like after these PIDs have been implemented, and you can see that the robot kind of stays with its feet on the ground, and it doesn't really have drift that is detrimental to its behavior. This is fairly effective. All right, so now that I've talked about kind of what my contributions have been so far, I'll talk about what we're still missing and what we plan to do in the future. So one thing is that currently, although we've increased the modularity of the framework, we still only work with walking and standing behaviors. So one future goal is to add the capability to walk while crouching by determining some parameters that we can give to the neural network to indicate that we want the robot to crouch. So to that end, we've already collected all of the data. You can see in the slide kind of what it should look like. This is from the data set. And yeah, we'll be working with that. The other stuff that I'm fixing right now is ready. And then the other thing is, yeah, right now, the way that the post-processing is organized, the linear and angular velocities are decoupled, so they're not processed in the exact same way. And this, because it's not consistent, it would be better to process them in the same way. So the other thing that we plan to do is to actually change the training such that the loss function incorporates the kinematically feasible constraints in like a soft constraint type of way. And this would reduce the amount of post-processing that we need to do and also kind of make the algorithm cleaner, let's say. So, yeah. Okay. And yeah, that's all I have. This is what I've spent a lot of time looking at for the past couple of months. And yeah, if anybody has any.
Jet.
Simulation.
Nice, with a jet like this. Any question for Evelyn? So there is this really nice, I don't know if you can get to the architecture when you added the PID. Yeah. So yeah, this was somehow an eureka moment for us because we somehow took the trained neural network on the motion capture data, but then we have to add these inputs. So the robot move forward, the more robot left or rotate. So in the inspiring paper of Mann, there was this cumbersome stuff of somehow the Bézier curve, so it was not really easy to deal with. Then somehow Evelyn was able to make this really easy idea of thinking, okay, so the network is telling me to go there, I want to go there, I simply create a dynamical system that bends the thing. But nobody really could have thought that by feeding this back to the network, because this is an ARCS model, so it gets it back, then everything would have worked. Okay, so no question, let's thank you again. And now from the cloud, I guess.
I'm here from the cloud. Okay, so this means that I have more time, Danny? No.
No, actually,
so we have to keep the time, the pace.
Yeah, exactly.
Okay, so good afternoon, everyone. So let's see what we have done in the last research increment related to the iFeel. So first of all, for the newcomers, especially what iFeel is. So iFeel, the idea of iFeel is to create a set of wearable sensors that are capable to send information to some algorithm, AI algorithm. that then they can create human statistics. They can, let's say, give information to avatars, and also capable to retrieve information from avatars and AI algorithms that are capable to get, let's say, feedback, in particular case, haptic feedback, but also different type of feedbacks to the human. Out of this, we decided some time ago to have an idea of startups, so spin-off out of this technology that can, let's say, be applied in several sectors in the real market. So we are more, let's say, concentrated at the moment in the industry and the healthcare, but everything can be applied in different sectors such as sports, tourism, entertainment, and research in general. Okay, so I decided to divide this presentation in the current activities. So there are mainly 5 activities that we are carrying on. So the first one is related to the iFeel wireless suit. So probably all of you have seen it in the lab. Currently, we are not doing new activities on this, but we are just using it. So any feedback, of course, guys, is always welcome. So we can improve it and we can plan, let's say, new activities on this part. But now, at the moment, we are not doing new things on this. Then we are working on the iFeel wired suit, which is mainly the working suit that we are, let's say, developing. So we are working on development, new design, and also the wiring. So we are trying to connect all the sensors in a proper way within the suit. Then we are working on the shoes, so the shoes that you know, but we are designing, let's say, new version of the shoes we call 2.0, the version 2.0. So it's a new force-torque sensor design that we are carrying on with the mechanical workshop and iCap Tech. And also we are working on the wearability because we would like to make them more, let's say, wearable for humans and more robust and easy to use for everyone. Then we are also working on the stretchable insole. So the idea is to create a different type of shoes that is more lighter, let's say, and easy to use for, especially for the for sport environment, for medical environment, and so on. And in this, we are working hardware optimization, we are working data analysis, and the integration in new type of shoes. Then we are doing a test campaign. So we are, let's say, doing some test campaign and also planning new ones. So we do some data processing of campaign that we have already done. We define new protocols for new test campaigns, and also we are working a lot on ethical committee to be able to create to make these campaigns. Then we also, let's say, in general, we work on software design in all the 5 activities, and also in product design and acceptability. Okay, so this is a list of the milestones that were open last time. So the blue ones are the milestones that we carried on from the previous research increment, while the black one are the one for the last research increment. We go through one by one, so this is just to keep in the presentation, but I'm not going to read now. And we divide it from iFeel and iFeel startups. Okay, so at the end of this each section, I'm going to show you the overall status, so you can get a feeling of the actual state of each part. So we had 2 milestones related to the wireless suit. So the first one was to assemble new iFeel nodes. That we did it, and we have at the moment around 50 units that can be used. So more or less 5 sets of full set of sensors that can be used in the lab. Then the second one was to write the paper on iFeel technology that I don't know, I keep on being optimistic, so I would like to say again that next research increment will be the good one, but I don't know. But yeah, let's try to do it before the ergoCub paper, Lorenzo, so I thought it was in the plan, so let's try to do it before that. Then this is the overall, let's say, the overview of the status. So we have a different type of suit of jackets that can be used. We have haptic feedback ready, and this is a small set of sensors that are ready in the lab. So we have, I think, double of these more or less available. Okay, moving on to the wire suit. We had this. The first milestone was to add wireless feature to the iFeel wireless suit firmware. So there was a long delay on the Nordic Wi-Fi development kit that we ordered, so it took like a few months to receive it because it was not possible to get in the market. We finally got it a few days ago, and we managed to test the Wi-Fi capabilities. So that can be implemented in our system. Now we move on to this real implementation in the hardware. Then we wanted to manufacture the stretchable connection for the field wire suits. So it's something that we would like to do it internally. We did it. We did the design. We sent it out, but the manufacturing process is quite complicated. They made several errors, and it took quite a while to finalize it. So still waiting for the device from the company. And then we had to design the wire node, so the unit sensor. We completed. This is done, and then is out for manufacturing. Then in few weeks we should receive the unit here in the lab. Then we had to design the field wired receiver. This requires some more time because we had first to test the Wi-Fi capabilities. So we did it, but now we start as soon as possible. We start the design of the wired receiver. Then we had to manufacture the enclosure for the field wired receiver. This has been done, it's been printed, but then of course we had to change the wired receiver. So we need to create a new one, design a new one, and print a new one. That is going to be the plan for the next research increment. Then we have to design the first prototype of the enclosure of the wire sensor. This has been completed. I will show you in the next slide what has been done in this regard. Finally, we have to get the field wire suit alpha prototype from Smartex, a company that we are working with to assemble this prototype. We are almost there. All the pieces are in pipeline. Some are already printed, but then we have to wait for the mechanical workshop to print the last 20 pieces to be able to create the first prototype. So this is an overview of what we have at the moment. So basically, you see the first prototype. This is not the right color. So this is just the first prototype done by Smartex. It's not completed yet because we are now applying this sensor that you see here. So basically, here you see what we have done, the PCB. So there is a PCB that is going to be connected to this enclosure on the suit, and then we are working now on the other PCB that is going to be plugged into this. So we are going to put around 20 of them for test purposes on the suit. But this is the work that we have done so far, and in let's say a few weeks everything should be ready, and the idea is to end of August to have the first prototype of the suit. Okay, then we move to the status of the shoes. We had to start the activity for the new version of the shoes. We decided to start an internal development, so we don't go anymore, at least for the time being, with an external companies. That was quite difficult, let's say, to understand, to show them what we needed, to explain what we need. So we decided to do it internally. We are currently working to create this new shoe. Prototype of the fish shoe 2.0. So this is everything is let's say the first part has been printed. The FT and the supports and the plates have been 3D printed. We missed some small details, so we are planning again somewhere at the end of August, beginning of September, to have everything ready for this. Okay, regarding the testable install, I'm not going too much in details because then Gianluca will give a presentation, vertical presentation on this. But then the idea was to integrate the SD card into the stretchable acquisition unit because we would like to record all the data related to the gate to create a proper gate analysis in an SD card. Still, we did the first investigation of this, but it's not completed. Then we wanted to calibrate the insole inside the pressure chamber. We decided to change the calibration strategy. I'm not going to spoil the next presentation, so Gianluca will give you more information on that later. And then we wanted to design the first prototype of the field sensor, which is basically the shoes with the stretchable insole inside. Then we had to write a first draft of stretchable insole paper. So we started. What we missed now is the calibration section because we moved to different type of calibration, so we need to change a little bit. Finally, we had to manufacture the field stretchable insole, the new version, 3 different types with 3 different companies. We opened the order, but there were a lot of issues related to the manufacturing process. So this demonstrates also the difficulty for companies to manufacture it because it's pretty new, let's say, process that they have to implement. Okay, this is just a quick overview. So here you see the shoes, the first prototype homemade, let's say with some data. You see the video later. And then you see the new approach that Gianluca is following for this calibration. But then we get more insight later on. Okay, then finally for the test campaign, we had to process the experimental data that we took at ISM, the first batch of people, so 7 people. We need to do other 14 people by the end of the year, so we need to finalize as soon as possible this post-process of data. We are working on the refactoring of algorithms to make it more, let's say, usable for all the data that we retrieve. But we are working on it, and we plan to do it again within a month or so. We hope to finalize this post-processing. Then we have to submit documentation to ethical committee for the clinical trials with San Martino and Villa Beretta. We are working on this. Protocol finalization is almost over. We have to do some other documents, but again, we are planning in the next month to finalize it and submit. Overview of the test campaign. We have a test campaign running on with the ISM that is going to end at the end of this year with 20 people involved. We are working on the multi-center clinical trial with San Martino and Villa Beretta. So is something that we would like to start at the beginning of next year. So the idea is to submit in September. Probably will take some more time because we have to pass also through the minister after the ethical committee. But somewhere in 2024, the first half of 2024, we would like to start. Then we have the test campaign that can start in Reporti Roma, so something that we need to discuss and plan when we can start it. And finally, we have first, let's say, a discussion with Ilex, is a company in Chiavari, close to Genoa, that they are, let's say, willing to start some collaboration with us, especially using our technology in their process line. So it's just starting point. So we see it takes some time, let's say, to finalize it. Okay, so finally for the startup, the idea is to organize an advisory board. We contacted some attendees, possible attendees. We have just to plan now the exact day and the place where to do it, and then I think is going to be done. So the idea is somewhere in September, October to do this advisory board. Then we have to prepare some documentation required to approach investors. This has been completed. We create some one-pager and some other documentation for the investors. Everything is ready. So now we can start the activity of presenting iFeel to venture capital to get funds raised and then start the company, hopefully. Okay, some statistics. This is pretty much in line with the previous one, so I would say nothing special on this. So it's the derivative, let's say, is very similar to the one of the previous research increment. Then here again is very similar to what we have done in the previous research increment, so nothing, let's say, special to say about this. Here instead we had a little bit less, let's say, little less percentage of tasks that have been completed. My understanding is that we had some more in this research increment. We had some more exhibitions and let's say show demos related to iFeel. So we lose a little bit more time on that. And also we didn't finalize few milestones simply because we are waiting for the external companies to conclude their job. Okay, so for the newcomers, please subscribe to LinkedIn, follow iFeel in LinkedIn, and then any question, I'm here.
Hello, everybody. Can you hear me? Okay, I'm Gianluca Milani. I'm a visiting scientist in the iFeel group. And this is what...
Gianluca is a long-standing collaborator on this visiting. Yes, he's just passed by, yes. He's there by chance.
And here is the iFeel vertical presentation, and I'm going to talk you about a lightweight capacitive-based iFeel shoe, which is not the one Daniele just showed. It's a parallel implementation that I will try to describe you today. Why? Let's start with the reason for this title. And basically, for those who do not know, iFeel shoes are a device which acts as a portable force platform. And it represents a fundamental tool in the iFeel system to perform articular stress analysis. Each shoe features two force torque sensors, which are able to measure forces and torques in three directions, X, Y, and Z. They are very precise. The only drawback is weight, which is quite high for a wearable system. Why this can represent an issue for the iFeel system usage? Well, let's think about the two main iFeel applications. Here you can see a patient affected by multiple sclerosis, which is performing a gait analysis test to understand the status of the rehabilitation process wearing iFeel. It's easy to understand that a heavy shoe can modify the way the patient walks and indeed the measurements, and so also the clinical analysis. In the same way, in the industry environment, for instance, it's easy to guess that a worker may not accept a too heavy shoe in his daily activity. So, starting from this need, a question arises. So, may we use the stretchable insole that we developed in the laboratory to move towards a more integrated, lightweight, and comfortable shoe, still able to measure the six-axis force and torques exchanged with the ground that are fundamental for our needs? Well, the starting point at the beginning of March was this. So the hardware of the stretchable insoles was ready. We have this insole with 24 capacitive-based sensors, more specifically parallel plate capacitors, which are able to measure the punctual vertical force in a distributed surface. What was missing? The challenge were mainly two. So integrating the insole into some shoes, and most challenging, getting an estimation of six-axis force and torque measurements only from capacitance sensors. The first step was integrating the insole into the shoes. Well, this step was actually quite easy and fast, but also effective. Well, the result is still a prototype that is quite rudimental, fragile, we have to say, but I say effective because in the end, we successfully managed to showcase it in some of the last lab demos, as you can see in the video on the right. Okay, but then the hard part comes. So we are how to estimate the six-axis force torque measurements only from insole capacitance data. Why am I saying that this was challenging to think about it? Because on one side, we have a shoe with two FT sensors, each measuring 6 components of force and torques. On the other side, we have a capacitance sensor insole with 24 pads. So at the first glance, the only FT quantity that seems estimable from the capacitance insole seem to be the vertical force, so the force in the z-axis. But what about the other two components of forces, y, x? What about the torques? At the first sight, they seem totally unrelated. Well, actually, the idea, maybe physics inspired, related to physics, which made us believe this was possible, was the following. What if we try to relate the measurement of each FT independently to a set of sensors, not sensors taken independently, but a set of sensors which surround it. In other words, may a set of capacitance sensors surrounding an FT hide some information about all the FT components? Maybe, I don't know, thanks to its spatial distribution. Okay, nice idea, but we were missing a tool to perform this estimation. At that point, Daniele said, okay, but why don't we just try to apply the work Ehsan did back in time to model the FT sensors via nonlinear polynomial functions? And that's what we tried to do in the very next days. So the process was a three-step process composed by dataset acquisition, training of the model, and validation. In the first step, for our application, we had to acquire simultaneously datasets coming from the insole and from the FT sensors data, such as it can be seen in this video, with different subjects to have a good range of all the possible weights. Here you have the insole shoe over a sole with FT sensors. And here a graphical representation of the signals you get from this dataset acquisition. On one side, capacitance, on the other, force and torques. For the Ehsan model, the capacitance signals represent the inputs, the quantities that you have, that are available, while the forces and torques represent the ground truth. And so in the training phase, we had to train this nonlinear model, which has 12 inputs and 6 outputs. If we go a little bit more in the specific and into the mathematics, we have that if we call y the output and u the inputs, the algorithm, what is going to do is going to try to find the best, the coefficient alpha, beta, and gamma, which best approximate this equation. This is the quadratic formulation, but the algorithm Ehsan developed allows to modify the parameters and going also quadratic, cubic, and choose the polynomial grade you prefer. And it allows actually to combine all the inputs to get the 6 outputs. So after the model training, a validation has been run using brand new datasets. Surprisingly, I have to say, the fit was very good. So the blue curve represents the estimation, and it almost perfectly overlaps the measurements from the FT for all the 6 components, so force and torques in the X, Y, and Z directions. Yeah. This means that theoretically these coefficients, the coefficients the model found, can be theoretically be used to substitute FT shoes with insole shoes. This for sure has to be considered a preliminary result. But okay, let's say that we once again we have to highlight, in my opinion, the importance of integrating and interfacing between each other, as in this case with Ehsan, no? With different research lines. That seems far away, but maybe they can find allow to reach a nice result. So next steps, which can be for sure creating a more robust shoe prototype, maybe with the help of a product designer like Gianmarco, and and then perform a new training with the new shoes, and finally, hopefully, a test with on the iFeel suit application to see if it everything works fine. Thanks.
Thanks, the visiting scientists that just passed by. So, any question for Gianluca? Giulio has a question. Yes.
Ciao. Yeah. So, I mean, okay, given the results, seems everything is working, but it's not clear to me how it's possible to estimate the X and Y component using only the FZ, because in the end you have FZ plus the information on the distance. So that is given by the topology of your insole. But Fx and Fy, and from literally, from mathematically speaking, it's not clear to me how it's possible that you can find them.
Okay.
I don't know if you can comment.
Actually, that's the thing. The first thing I told Danny when we first look at the results, and I said, okay, but it's something very strange, no? It's amazing, but strange to me, no? That everything was so easy, no? And Danny answered, okay, this is the magic of nonlinear models.
Oh, yeah.
But okay, yeah.
Probably you can also show the.
No.
I mean, there is the physics here. That
No, yeah,
can you show the real? Can you show the real insole?
The real.
Because this is.
This was my interpretation also, because as what also we said before also, no. So the fact that having distributed sensors can maybe in some way hide some information about some other components of forces.
Yeah.
Danny was wondering also about the fact that the insole can actually stretch. So this is a stretchable material. I don't know if I interpret well.
Yes, I mean, because clearly, if can you stop here? Yeah. Theoretically, these are not really like isolated paths vertical. So when you have a tangential force, all these little stuff change. So they actually influence a little each other. So the physics of this, you're dilating, you're increasing the distance between a little bit this stuff. Okay, so you are changing the signals, because clearly, Giulio, you are right. If it didn't exist a single signal that would vary if you apply a tangential force, this is not observable. That's it. But here the problem is that the physics of this machine that Gianluca made, and then Gianluca made it even more complex, because one day he said, "Oh yes, I made a shoe," and and actually the shoe was working out. So it's even more complex. Okay, so it's the physics. It's not the one that you have a capacitor and then you are measuring the distance. You have the capacitor, only the vertical force. No, here it's a mess. Okay, so it's a big mess. Okay, but the nice thing is that this mess somehow keeps and retains some characteristics from the noise to signal ratio, which allows you to be sensitive to tangential forces. So this is somehow the interpretation that I just fill up with more arguments, what Gianluca was saying. And this is the interpretation that we got, okay? That the physics of this device is a mess, but it was nicely designed so that you keep and retain nice properties from the noise to signal ratio, so that this signal is going to be sensitive to tangential forces. Okay, and yeah.
Okay. Now it's more clear. Yeah, thank you. It makes sense.
So I wanted to partially complement and partially make a question. So I was also wondering if maybe the information of the surface. So, okay, the point is that what Giulio was mentioning is correct as long as all the capacitance are in the same plane. So, but if while walking, say the shape of the person's foot deformates also 3 dimensions surface, then you have some capacitance that are not the capacitors are no more aligned all around Z. Some of them are have some tangential components. So, and the question: was it actually deforming, or the sole was very rigid, so that this could not have happened?
Okay, so you how to say? Okay, the sole is soft. You can see here the white layer is soft. Only my concern is that this is very thin. No? The actual capacitor is represented by this first assembly, no? So very thin, very thin structure composed by two conductive plates and in between the dielectric. So I don't know.
What Professor says that when you walk, do the relative orientation of this thing change with respect to the horizontal? So yes, so your thing is actually correct because everything is flexible. So when I put my 97.6 kilos on the shoe, actually this thing really change, and then it's a mess. The physics it's even a mess. So we said we put it together. Let's see what we get out of that.
I'm not quite.
Nice interpretation that if you stretch things, you're modifying the areas, and if you modify the areas, then as a consequence, you get an influence on the. This is actually Stephan's words. Just see it citing him. So, it's the physics is a mess. So
No, just a comment also on what Giulio said and Mohamed and Stefano. I think maybe one of the reasons why the results are good also for tangential forces is that, of course, this is not a stress test on a device that measures force. It's a test made on something that you walk in, and I mean naturally you don't express as much as force in the tangential force as much as you doing in the vertical one. So I mean I don't think it's comparable. I mean I think it's at least one degree of amplitude less. Yeah, it's friction, but I mean that may help the model to. So just to say, maybe. So, I mean, maybe this is also the reason why the model can compensate so well in the.
nice. So let's thank Gianluca again. Now it's time to lunch. So for all that do not belong to the AMI, thank you very much for being here. And instead for the other lab members, we meet for the planning at 2:30.